Welcome to this presentation about IoT Vertebrae, a system able to emulate an industrial PLC, a system able to emulate what is an industrial PLC. It is thought for bridging operational technology and information technology. It is convenient for Internet of Things, for projects with a lot of inputs and outputs. This is just some of the concepts. There are signal levels are industrial ones, 24 volts for digital inputs and outputs. It can be other depending the power supply of the RIPs. The analog inputs are from mains 10 volts to plus 10 volts, and analog outputs from 0 to 10 volts. And here there are some blocks in a snap just able to interact with this board. Then the concept head. The head is just now today is an MQTT translator to backbone. This is the backbone, and now we're using a bus called CAN bus. The backbone is the set of vertebrae boards connected through a main bus. These are the RIPs. The RIPs are flagged to vertebrae sites. You see that there are site B and site A in this set. The address is selected by hardware using this kind of connector. The jumper on means 1. In this case, we have just the address all zeros, is without jumper. In this case, it would be 0100. The site is just the site where is the RIP, A or B, with what is connected at the vertebrae. Then we have the value. The values, there are two types of values. The digital ones are zeros and ones when they are sent like a byte. And here we're using just a level of bit, and then the value is 0 or 1. When we are using, when we want to send analog output, we are sending values from 0 to 4095. And when we are just reading, this block is a reporting one. This is analog input. We are getting values from 0 to 30,000 approximately. Then the bit is when we are just going to a bit level. We are saying which is the bit. There are 8 bits for digital outputs and inputs. And this is from 0 to 7. And the channel is used for analog inputs and outputs, that they are 4 channels. Then we have the blocks. The out is for digital outputs. We see here, we write the address, the site, and the value. Digital input is a reported block that is given by the address and the site of the RIP. We have analog outputs, like here. This is the address, the site, and which is the channel, and the value we are sending. And analog inputs are reported blocks, just getting the analog input. There are other ones like the out bit that is just sending bit by bit, and the out PWM because we can send PWM signals. Here there is what we're about to show today. This is the boards. This is just the head, and here is the power supply part. We have here an analog output board, here an analog input board. This is just digital outputs, 0 and 24 volts. They are acting as relays. And here we have inputs, that digital inputs that are 0 to 24. The main bus is based on Olinex bus. That is a standard of this Bulgarian brand. And what we have done is just an extended version. We have added here just for the CAN bus connections and the power supply. We're using 2 kinds of buses. One is I2C bus that is useful when we have all the vertebrae just connected, and we can use another bus, that is the CAN bus, that is the bus used for automotive industry in cars, and this allows to have vertebrae just far away from each other. In this session, we are about to use some of these peripherals. We have a hair dryer, bulb lamp, an emergency stop button, sound and light alarm, and a 24 volts power relay. And then this is just a dimmer. We can dim the bulb light or just the power of the hair dryer. Then here we have the power relay, can be controlled with a digital output of 24 volts. And with this, we are able just to control directly the light of the bulb light or the hair dryer or this alarm. In this board, this is just digital output using a snap. This is just the digital vertebrae. This is the rib. The address is set in this connector. Bit with jumper is 1. Bit without jumper is 0. Site is where the rib has been connected. In this case, we can see that is the B site, and the values are 8 bits. 1 is relay on, 0 relay off, and it's from 07 to 00. Here we have the digital output using just the out bit, that it is just sending a bit from 0 to 7, a value 0 or 1. Just for the input, we can use this emergency stop button, and it is connected in one side to 24 volts. The other side is the input, and when we press, we are able to read if it's pressed or not. Just to use the proper lock is the in. With this here we have just connected at the A side, and it's just as before. When we are reading, this block is reporting 8-bit value byte. This is just the dimmer with a level of voltage between 0 and 10. We're about to dim this bulb or this hair dryer. Just to set analog values, we have an analog vertebra connected in this case to the B side, and these are outputs. We set the address with this connector, and we should say which is the site, which is the channel. We have 4 channels giving a voltage between 0 and 10. When we are sending 4095 is 10 volts and 0 is 0 volts. And then just to read the analog values, we can use a current loop tester, or we can use anything that is giving us a voltage between -10 and 10 volts. Then just to be able to read, we have this 4-channel analog read board that is connected in the other side, in the side A, and here we have a reporter block that is giving us, we are giving the address, the site, and which is the channel. And this is just now the trial that we're about to do just now. I don't know if Xavier is able to share the camera. Xavier? Are you over there? Are you listening to me? I have no interaction now. Okay, then I expected just to have a camera just pointing to the board and to be able to use a snap to control the board remotely.
There is a camera.
There is a camera. Okay, I am not able to see this camera, but okay. Then this is just a snap, the snap blocks. Here there is the detail. This is the setup block that we are connecting to a broker, and every board has just a MAC address, and then we connect to the broker using the MPDT blocks developed by Simon and Xavier. And here we have just the blocks, and we can analyze the out block. That is this. Then this is just using the CAN standard with the CAN values, and then we are translating what we are writing. Just a lot of echo. And I don't, maybe I can use the chat. In any case, I am about just to connect, just doing the setup, and then I am just clicking on the digital out. I am sending just a one. I am not able to see just the, yes. I am not listening anything. I don't see the camera, but now I am sending all ones. I don't know if you are able to see these ones. And now with this, now what we are doing is just lighting the LEDs off. Now what we are about to do is just to send this one, and we're about to read the value. We see that the word has a one. Now we're sending all zeros, and then I expect here to have all zeros. Now we are just reading the digital inputs here. Now we're about just to click on all the 4 analog outputs. I am writing 0, and now I am about to read this value, and I see that the value is 13,000 more or less. And this is because minus 10 volts is just 0 volts. Sorry, minus 10 volts is just a 0 number, and just in the middle there is like 26,000 plus 10 volts. Then when we are sending 0, we are reading this value. Now I am about to send 10 volts, sending 10 volts. Now I am reading 26,000, and now I am about to send 2,000, that it's more or less 5 volts, and I expect to read here this value. Now I am reading 20,000, okay? And then again, I put the maximum, that is this one, and I'm reading this. Now, we can send just bits using the out bit. Now I am just lighting one LED on, and with this is off. And now the next trial is just to push the emergency stop button. And then we have here Alonso now, and I expect just to change when we push the button. I am just clicking on this loop, and now Xavier just presentially is just pushing the button. And I guess this is just everything that we wanted just to explain today. And you have in the materials just a longer presentation, just with more explanations about every vertebra and about every rib. And then if you want, now is question time. Do you have any question? I am not listening, nothing at all now.
There's some questions on the chat, like if you're going through MQTT, is there latency? And then what processors do you use on the vertebrae and what's expected to be connected to the head?
Okay, then I am going to the presentation. And here, all the chips used in the vertebrae are an ESP32 and S3. And just for the head, we are using an ESP32. In this case, just the head is designed to connect to the backbone using this connector. And this other connector is just to connect Raspberry Pi. We can use I2C from Raspberry Pi to be able to control everything. We have designed, and in the GitHub, there are some Python codes able to control through I2C all the vertebrae. In this session, we have used just another channel that it is the CAN bus, and then what is doing the head is translating MQTT protocol to CAN bus protocol, and is what we are using here. And then this is just the design of the head. Here is the ESP32, and if we're going to the digital vertebra, this is the version 1.0. We use just a normal chip, but we had the need to use PWM. Pulse width modulation, and then we changed this chip for an ESP32 S3, and we have added just the CAN bus connection. We can use just the chip, the CAN bus chip, or here just a module. And here, this is the picture of the ESP32 S3, and in the analog vertebra. We're using this ESP32, and here there is just a converter from 24 volts to plus minus 12 volts, because the analog grips are able to read from minus 10 to plus 10 volts. This is just the RIP that we're using here, just a popular module, and we're using this supply is here.
And then one more question, since the summary talked about microblocks, there's a question: have you used microblocks to control your vertebrae or your head, or what are you using to control those?
We have used microblocks in another board, just an educational one, and with the help of Bernat. And now we are working in some boards, extra boards that we need for next projects, but we expect just to include microblocks inside. Overall, just the best part to program microblocks is in the head here. And then we, in the future, we will have just some codes using microblocks to control the vertebrae. I don't know if this answers your questions.
We're over time.
Yeah, great. Thanks. Great project.
Okay, thank you very much. Then this is everything. Shalom. Goodbye.